Hi, in this last introductory video we're going to go over Taylor series applications, and we're going to focus on how the calculations of the error are going to work out for approximating functions via polynomials. So the most important use of Taylor and Maclaurin series is going to be to convert any function that has a power series representation into a polynomial that can reasonably approximate where the power series is going to converge. For example, we have a value that can be very difficult to compute with our calculator, like sine of 3, but at the same time we could use the power series and do an approximation that we could do by hand. Like, for example, we're approximating here with a polynomial of degree 5 using 3 terms of the power series. And this will be 3 minus 3 to the cube over 3 factorial plus 3 to the 5 over 5 factorial, which is the Maclaurin series for sine of x expressed as a reasonable approximation of sine of 3. Now, if you recall, the Taylor polynomial function of a given function f is going to be given by the expression Tn of x being f of a plus f prime of a over 1 factorial x minus a plus f of 2 prime of a over 2 factorial x minus a squared, and we keep adding up to the point where we get f of n or the n derivative of f plug in a over n factorial times x minus a to the n. We're going to use this polynomial to approximate any f with a power series expansion. But how good is going to be this approximation? What bound is the error going to have? We have a couple of options to actually check on this. The first one is, of course, if the series is going to be alternating, which is a case that can happen a lot. Then we can use the alternating series error, where we know that the error of the approximation of the polynomial is going to be less than the n plus 1 term. Now, or the next term in the sequence according to the approximation that we're using. Now, the second alternative is we can use the general Taylor inequality that says that if the n derivative or the n plus 1 derivative at a certain point x is less than a constant, or we can say that the n plus 1 derivative is bounded, then the error term of the polynomial approximation is going to be less than that bound m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. Now, but how this works in practice? So let's see an example of this for approximating a function with a polynomial and to checking how accurate this representation is. And here we're going to consider the function f of x equals cube root of x, and we're going to approximate this function f by a Taylor polynomial of degree 2 at the point a equals 8. And we want to check how accurate is going to be this approximation if we are in a radius of convergency 1, so we're moving between 7 and 9. Now, on the first thing that we have to do is, of course, find the coefficients from our Taylor polynomial. And so we're going to find, we have f being the cube root, so f prime is going to be 1/3 x to the minus 2/3. The second derivative is going to be minus 2 over 9 x to the minus 5/3. And the third derivative is going to be 10 over 27 x to the minus 8/3. And this is something that you can double check very quickly if you want to do the calculation by yourself. Now, if you just find the coefficients that you need for a polynomial of degree 2, you only really need f of a, f prime of a, and f2 of 8, since those are the ones that are going to be enough for a polynomial of degree 2. I'm going to use the number 3 just for the fact that I have to bound the derivative for the next term. Now, the second degree polynomial then is going to be f of a plus f prime of a over 1 factorial times x minus a plus f2 prime of a over 2 factorial x minus a squared. Now, replacing that by the values, that gives me this polynomial 2 plus 1 over 12 x minus a minus 1 over 288 times x minus a squared. This desired approximation here for square root of x is going to be pretty good. And we're approximating the function, but we also got to check what happens with the error. See, the error is going to be the difference when we're computing in a particular point, the difference between the actual function and the polynomial approximating. So now, according to the information that we have from the options for error, because the Taylor series is not alternating with x is less than 8, we can really use the alternating series estimation. And so we can just use the Taylor inequality when n is equals 2 and a is equals 8. So we're going to have this set up where we have that the absolute value of the error for polynomial of degree 2 is less than a certain constant m over 2 factorial times x minus a to the cube. Now, together with that, we want to explore what m is going to be. And we know that f3 prime got to be less than certain m. And this is going to be true in particular because when x is bigger than 7, so for example, from 8 onwards, we can have that x to the 8 thirds is going to be bigger than 7 to the 8 thirds, which is just given by the fact that the powers are increasing. And so taking into account that I know that the derivative is 10 over 27 x to the minus 8 thirds, then I'm going to flip around those values. And then I'm going to have that in general, f3 prime is going to be less than 10 over 27 times 1 over 7 to the 8 thirds. And so that's going to give me that f3 prime is going to be less than 0.021. So it's giving me an upper bound for the third derivative. Now, once that we have this value, then I can just plug it here. And I'm going to have a very specific bound that I can use. Now, also, if x is between 7 and 9, then I can say that x minus 8 really is between minus 1 and 1. So this will be saying, well, the radius of convergence here is 1. X minus a is less than 1. And so the Taylor inequality here for the residual is going to be less than 0.0021 over 3 factorial times 1 cubed, because this, remember, x minus 8 is power to the cube here on this inequality that we're using for the error. So now this is going to be equals to 0.0021 over 6, which is less than 0.004. So in general, if x is between 7 and 9, this approximation that we have in part A is going to be accurate within 0.004 of error.